Hello everyone. A very good evening to all of you. How are you all? Yesterday we did not have the class, right? So before moving on to the class, I would like to launch a poll to check the class status. I have launched it. Please let me know your answers in the poll. Am I visible and audible? Am I visible and audible? So only 50% of the answers I have got. Yeah. Now I am getting. Yes? Okay, great. So now let's move on to the session. So in the last class, what we have discussed, what is the name of the topic that we have discussed in the previous class? Can anyone tell me what we have discussed, my dear students? Yes, Ganesh. What we have discussed? Very good, Bhagat. It is crystal field theory, right? Good. We have discussed the crystal field theory postulates, and we have discussed the octahedral splitting, tetrahedral splitting, and its related informations on Tuesday's class, right? So one more small topic in the crystal field theory is left out in that day, right? So it is the color in the coordination complex. So I have already told you that valence bond theory was unable to explain the color of the coordination compounds, but crystal field theory was able to give the explanation about the color. Okay, so let's see. Let's see how the crystal field theory is explaining the color of the coordination complexes. So the color explained by CFT, crystal field theory is, so let us take one complex. To understand the color concept, we will take one complex, one titanium complex we'll take. Titanium hexa aqua 3+ complex. So can you find out the oxidation state of titanium here in this complex? Actually, this 3+ has to go here, 3+. Okay. What is the oxidation state of titanium in this complex, students? Give me the answer fast. Very easy, no? Yeah. Very good. It is +3. Since water is a neutral ligand, no charge for it. So the oxidation state will be equal to just the charge on the complex, which is 3+. If it is 3+, how many d electrons will be present for titanium? What is the configuration for titanium first of all? It is 3d2 and 4s2. And if titanium is present in its 3+ state, how many electrons we have to remove? 3 electrons we have to remove. 2 electrons we have to remove from 4s orbital and 1 from d orbital you have to remove. So remaining 1 will be there in the d orbital. So 3d 1 and 4 is 0. Okay. So in the 3d orbital we have 1 electron. Now according to crystal field theory, octahedral complexes will have octahedral splitting, right? Since we have 6 H2O molecule, it is an octahedral complex. So octahedral splitting will be 3 below and 2 above. So the first 3 orbitals will come down, the T2G orbital will come down in energy and the EG orbital will go higher in energy, right? And the 1 electron which is present in the 3D orbital will go to T2G. Now, this 1 electron which is there in T2G will absorb some energy. Will absorb some energy, h nu amount of energy, light energy. Okay, in the blue-green region, it will absorb. And after absorbing the energy, the electron from T2G will jump to EG orbital. It will jump to Eg orbital, and the configuration will become like this. Okay. Now what will happen? The energy which has been observed by the electron will be released by that electron. The same amount of energy which it has observed will be released. Okay. And this electron will come back to its original position. And that released energy will go and fall in the visible region of the electromagnetic spectrum. And because of that, we will get the color. Visible region means we will have VIBGYOR, right? Visible region has VIBGYOR kind of color things, and so that this leads to the formation of color for coordination complex. And the color of this particular complex is violet. Okay. So the electron is moving from one d orbital to another d orbital. Electron is also called as a charge, negative charge, right? So the d to d charge transfer, or the dd charge transfer, dd transition is happening here. So the color is produced for a complex due to the dd charge transfer. Clear for all of you? Clear? Can you all able to understand that how a color is being formed for coordination complex? The metal has d electrons in it, and when by the jumping of this electron from the lower energy to higher energy, the color is produced. Okay? Clear? Shall we go for the next slide? Now, who is inducing the color? Who is inducing? Who is giving the color to the complex? It is the ligand. Okay. So ligand is inducing the color to the complex. So let's see the influence of ligand on the color of the complex. So to understand this influence of ligand, I'm going to take a nickel chloride complex. Okay. So to form the nickel chloride complex, I have to take the nickel chloride salt and I have to add water to it. So if I add water, all the 6 molecules of water will be bonded to nickel. And the color is green in color. Color of the nickel complex here is green. Now, to this complex, if I add ethylene diamine is a ligand. It is a bidentate ligand. Ethylene diamine is a bidentate ligand, right? So what this ligand will do? It will go and kick out 2 water molecules from this complex, and one ethylene diamine will take the place of 2 water molecules. So that we will get nickel H2O 4 times and ethylene diamine 1 time. Okay. Now you see the color has been changed from green color to pale blue color. Okay. So if the ligand is changing, color is also changing. All right. Now what I'm going to do, I'm going to add one more ethylene diamine to this pale blue complex. So what this another second ethylene diamine will do, it will kick out the next 2 water molecule from this, and it will go and take the place of those 2 water molecules. So that we will be left only with 2 more, and we are having 2 new ethylene diamine now. Now the color has been changed from pale blue to purple. Okay. Then on adding one more ethylene diamine, the last 2 water molecules is also kicked out, and all the ligands are now ethylene diamine ligands. Color has been changed from purple to violet. Okay. So here in the slide, this color is looking like a pink color, but a kind of violet. Okay. It is a violet color. So now, if I change the ligand, color of the complex, color of the solution is also changing. So who is giving the color to the complex? Ligand. The color of the complex is based on the ligand. Clear? Clear for all of you? Ethylene diamine is a strong field ligand. Ethylene diamine is a strong field ligand. So the energy separation will be more and it will absorb more amount of energy and it will give a color. Okay. Shall I go for one question from this concept? I'll go for one previous year question based on the color concept. So here we have three complexes. All the three are the complexes which we have studied now in the previous slide only. Okay. So we have to find out the order of energy observed which is responsible for the color of the complexes. The order of energy observed which is responsible for the color of the complexes. Can you find out the answer for this question? So I will give you some 30 seconds to solve this question. So let us see who is giving me the correct answer. Let's see who is going to give the correct answer. I am waiting for your answer, students. You need to give me the answer first. Then I will ask you the question why. Okay, so you need to be prepared for giving me the explanation also. Okay. So which option is correct? Which compound will absorb more amount of energy? Find out the answer fast. Students, what is the answer for this question? Which option is correct? Which option is correct? Not even a single student has got the answer for this. Oh, great, Bhagat. You have found out the answer and your answer is exactly correct. Option C is the correct answer for this question. Very good. Very good. Can you tell me why option C is correct? Can you tell why option C is correct? Okay. So, because ethylene diamine is a strong field ligand, it absorbs more amount of energy. So, in compound 3, we have 3 ethylene diamine. In compound 1A, we have 2 ethylene diamine. And in compound B, we have 1 ethylene diamine. So, what will happen? Where we have more number of ethylene diamine, in that case, more amount of energy is observed. Okay. So, ethylene diamine is a strong field ligand. Water is a weak field ligand. So, strong field ligand will absorb more amount of energy. Since more number of ethylene diamine is in compound 3, it absorbs more energy. Then comes A, then at last only B will come. Okay. So, the correct order is option C. Very good. Very good. Great. So, now we will move on to the next topic, the last before topic of this lesson, which is bonding in metal carbonyls. So, we have completed Werner's theory, valence bond theory, and crystal field theory. So, now we are going to study the bonding in metal carbonyl, which is a very small topic. Okay, it is a very small topic. And after this, we have one more small topic, and with that, the lesson will get over. Okay, so let us study the bonding. Let me take the structures of some important carbonyl complexes. Before moving on to the structure, we should know what is a metal carbonyl complex, right? Can anyone give me the meaning for this? What is a metal carbonyl complex? What is a metal carbonyls? So the complexes which have carbonyl molecule as a ligand. Complexes which have carbonyl molecule as a ligand are called as metal carbonyls. What is the formula for carbonyl molecule? It is CO. The formula is CO. So now I will go for some examples. So first I will go for the metal as nickel. So nickel carbonyl. Nickel tetracarbonyl. So which is tetrahedral in structure. And then I will take one iron complex, FeCO5, iron pentacarbonyl. So it is trigonal bipyramidal in geometry. So this is trigonal. And if I connect all the three to the above CO, I will get one pyramid. And if I connect all the three which is there on the plane to the below CO, I will get another pyramid. So it is trigonal bipyramidal in structure. And the third example is CrCO6, chromium hexacarbonyl. So I have 6 ligands, 6 CO here. So 4 are there on the square plane, 1 above and 1 below. Octahedral geometry. It is octahedral in structure. Okay. And the next is Mn2CO10. So 2 manganese and 10 CO we are having. Okay. And each manganese if you take, they will have octahedral geometry. So 1 above and 1 below kind of thing. So it is kind of octahedral. And lastly, CO2CO8. So 2 cobalt metal atom. And this CO is different from this CO. Okay. This is a ligand. Both are capital letters. CO capital. This is a ligand. And this is a metal. This is a metal atom. Capital C, small o. Okay, this is a metal atom and this is a ligand. Don't get confused with both CO. Okay. So these are some of the structures of carbonyl complex. So now in all these cases, if you see, we have a bond between the metal and the carbon. We have the bond between the metal and the carbon. Okay. So now we are going to study the bond which we have between the metal and the carbon in all the cases. Okay, let's see. Let us go for the bonding. So first of all, you should listen properly, then only you can understand. Okay, otherwise it will be difficult. Listen. So I have a metal. Metals will have d orbitals. Okay, 5 d orbitals will be there. Some of the orbitals may be filled and some of the orbital may be empty. Okay, so metal is having orbital. So this is one of the orbital. The pink color is one d orbital and this d orbital is filled. Okay, this d orbital is filled. And the carbonyl ligand is also having orbitals, bonding and anti-bonding orbitals. So the pink color is anti-bonding orbital. The pink color is the anti-bonding orbital, which is empty. So now what this metal will do, since the metal is having the filled electrons in its orbital, it will donate those electrons to the empty orbitals of CO. Okay, the filled orbital of metal will donate the electrons to the empty orbital of carbonyl ligand. Okay, and it will lead to the formation of pi bond. So why it is leading to the formation of pi bond? We have sideways overlapping, right? Here the sideways overlapping occurs. So I have the formation of pi bond from the filled to the empty metal orbit, empty ligand orbital. Okay. And now next what happens? Carbonyl ligand has bonding orbital. This is a bonding orbital which is filled. And the metal is also having some other orbitals which are empty. Now the filled orbital of the ligand will donate the electrons to the empty orbital of the metal in a head-on manner, leading to the formation of sigma bond. Leading to the formation of sigma bond. Head-on overlapping means it is sigma bond, right? So the donation of electrons from carbonyl ligand to metal by sigma bond. So this green color shows the donation of electrons for the formation of sigma bond. So what do we understand from this? The metal carbonyl bond possess both sigma and pi character. The metal carbonyl bond possess both sigma and pi character. Okay. So this particular bond has both sigma and pi character. So because of this character, the bond is getting strengthened. Okay. The bond will become very strong. The metal carbon bond becomes very strong in that case, so that it is highly stable and it cannot be easily disturbed. Okay. And this effect is called as synergic effect. And we call this type of bonding as synergic bonding. And this synergic effect is strengthening the metal carbonyl bond. Okay. Synergic effect is strengthening the metal carbonyl bond. Okay. Clear? So only 2 points you have to keep in mind. Metal carbonyl bond possess both sigma and pi character, which is leading to the strong bond nature of metal carbon bond. Okay. So this is all about the metal bonding in metal carbonyls. So do you have any doubt from this concept? Do you have any doubt from this concept, students? Do any of you have any doubt? Bhagat, Bishan, Christina, Ganesh, JNB Ramnagar students, Rahul. Okay. So this is all about metal carbonyl. Now let's go for the last topic of this lesson, which is applications of coordination compounds. So where do we use this coordination compound? So we use this in many areas. First is, it is used to estimate the hardness of water. So in hard water, we will have magnesium, calcium ions. Okay. So it is tight, it has to be removed. Hard water has to become soft, then only we can use that for drinking purpose and for other purpose. Okay. So the hard water has to be turned to soft water. So for that, I need to remove the magnesium 2+ and calcium 2+ ions. So for that, what I have to do, I have to titrate this with sodium ethylene diamine tetraacetate complex, sodium EDTA complex. So by treating this with by titrating this with sodium complex, stable complexes of calcium and magnesiums are formed. Stable complex. I will show you the formula. So here you see, this is actually the weaker complex. After treating this complex with magnesium 2+ or calcium 2+, we are getting a magnesium EDTA or calcium EDTA complex, which are highly stable. So the calcium and magnesium will go and form the bond with EDTA. Now they are no more there in the water. They are no more there in the water. And now the water is free from magnesium 2+ and calcium 2+ ion. And now the water is called to be a soft water. And we can remove this complex from the water using some other techniques. Okay. To estimate the hardness of water, we can use the coordination complex. And secondly, for the extraction process of silver and gold. So silver, you all know, silver and gold, they are not present in the earth in the native form, right? So it is present in its ore form or some other form. We have to extract the pure metal from the ore. Okay. For that, we need to go through some more steps of reactions. Some more techniques are there. Some more processes are there to follow to get the pure metal. Okay. So in that one among the process, we will have gold, and that gold will be treated with sodium cyanide and water, and it will form a sodium silver cyanido complex with NaOH. Okay. The same way, silver will also form a silver cyanide complex. So these two complexes, okay, in these two complexes, if you see, we have a silver and the gold. Now this is a coordination complex. This is a coordination complex, right? So this coordination complex can be further treated with the other compound, which is zinc, and the pure silver and gold metal can be extracted. So to get a pure silver and gold, we are doing some reactions. Okay. So in one of the reaction, the coordination complexes form. All right. In the extraction process, we are using. Then thirdly, it is used for the purification of metal. The impure nickel is getting converted to nickel tetracarbonyl by the treatment of 4CO ligand. If the impure nickel is reacting with 4CO ligand, it will give nickel tetracarbonyl, and on decomposition, nickel tetracarbonyl on decomposition will form a pure nickel. Okay, so for the purification of the metal, we are forming or we are using the coordination compounds. Okay. Then the biological importance you all know. In the beginning of the lesson itself, I gave you, right? So in the chlorophyll is a coordination compound in which magnesium is present as a metal, and hemoglobin, iron is present as a metal, and in vitamin B12 complex, we have cobalt present as a metal. Okay, so these are all the biologically important complexes. Then it is used in the enzymes also. In case of carboxypeptidase A and carbonic anhydrase enzyme, we have zinc metal as the metal atom in the coordination complex. Okay. Zinc is present as a central metal atom in the coordination complex of both the enzymes. Now, next is the industrial importance. So, in the industry, for the hydrogenation process, hydrogenation means addition of hydrogen to alkene. Alkene means it is a double bonded system. For example, if I have CH2 double bond CH2, and if I try to add hydrogen to it, I have to break this bond and I will add the hydrogen. This process is called as hydrogenation. Now, here for this process, this particular catalyst, which is called as Wilkinson catalyst, is used. And in this Wilkinson catalyst, you can see that rhodium metal is present as a central metal atom. Rhodium metal is present as a central metal atom. Okay. Rhodium is present as a central metal atom, and this is a Wilkinson catalyst you need to memorize. Okay. Rhodium tris triphenyl phosphine chlorido complex. You have to memorize that because they will ask you. And the reaction is also given to you, the same reaction which I have given here. Okay. Ethene on adding the hydrogen will form ethane. We will have C2H6. All right. So Wilkinson catalyst is used, which is a coordination complex in the industry. Then sixth uses the electroplating with silver and gold. Electroplating with silver and gold. So it is a solution actually. Okay, in the car and all, if you see, they will electroplate the car. So to prevent the corrosion, they will do this process. So in that solution, silver cyanide and gold cyanide will be present as one of the component, which is actually the coordination compound. Okay. So the electroplating is done with complex solutions like silver cyanide and gold cyanide. I mean, AU is gold, okay? Gold cyanide and silver cyanide, which makes the coating even. To prevent the corrosion and to make the coating even, they do this electroplating process, which is done with this type of coordination complex. All right. Then the next is black and white polarography. So you all might be aware of the olden days photography things, right? So there will be a film. So it is an undecomposed AGBR on the film. So that we have to wash and take away this AGBR. So to wash the AGBR, I mean to wash the film with the hypo solution. So the silver thiose complex is the hypo solution. Okay. So if we wash this undecomposed AGBR which is there on the film with this hypo solution, we will get the correct colored photo. Okay. So in olden days, they used to wash the photo with a solution, and that solution is an coordination complex. That solution is a coordination complex. So the straight away this undecomposed AgBr cannot come out from the film. But once you form AgS2O3 twice complex, that can be easily washed away. So to make the process easy, we are forming a coordination complex. Silver with the thiosulfate solution. Okay. Then next, the very important uses, it is used in the chelate therapy. Coordination compounds are used in the chelate therapy. So suppose if excess of copper is there in our body, what they will do? So the excess of copper is removed by the formation of coordination compounds with the D-penicillamine medicine. Okay. And the excess of iron is removed by desferrioxim B by formation of coordination complex. And if the lead poisoning occurs, then it is removed by EDTA complex by the formation of lead EDTA complex. Okay. So they will add EDTA so that the EDTA will go and form the bond with the lead and it can be removed out from the body. Okay. And at last, cisplatin. Cisplatin structure is here. It is a platinum complex with 2 ammonia and 2 chlorine molecule. So cisplatin is used to inhibit the growth of tumors. Cisplatin is used to inhibit, to stop the growth of tumors in the cancer treatment. They use this cisplatin, which is a coordination. Okay. So this last use is very important. Cisplatin is used for treating the cancer to stop the growth of tumors. Okay. So this is all about the uses or the applications of coordination compounds. And with this, we are closing the coordination compounds lesson. Okay. So thank you so much for listening the coordination compounds. So now let's go for the new chapter. Are you all ready to listen the new chapter? Yes. Shall I start a new chapter or shall I go with some previous year's questions? What do you guys say? Shall I go for the previous year's questions of this chapter, students? Are you all ready? Shall we solve it? Yes or no? Christina, Priyadarshini, Bishan and Jain B. Ramnagar students. Okay. So just wait for a while. Can you all able to see the screen? Can you all able to see the screen? Yeah. So I have got a question for you. So the homoleptic complex from the following complexes. So I just want to say this because I did not cover this in the class. Okay. Homoleptic means if the similar type of ligand is present inside the coordination entity, it is called as homoleptic complex. Okay. And also we have one more type which is called as heteroleptic complex. So heteroleptic means two different types or more than two different types of ligands will be there. And those complexes are called as heteroleptic. Okay. So now you can able to understand the difference between homoleptic and heteroleptic, right? Similar type of ligand means it is homoleptic. And if two or more than two types of ligands are there, it is heteroleptic. Okay. So which is the correct answer for this question? Which among the following is the homoleptic complex? So here we have diamine NH3 two times diamine chlorido and nitrito NO2 is nitrito N platinum complex. Okay. So here we have three types of ligands. So this is not a homoleptic complex. Okay. Next, coming to option B, we have pentaamine. Pentaamine. So penta means five. So 5-amine carbonato. Carbonato means CO3. Carbonato cobalt 3 chloride. Cobalt 3 chloride. Okay. Only one chloride will be there. So here also we have two types of ligand. So it is also not the homoleptic complex. Next, coming to option C. Triamine. Tri means 3-amine. Tri-aqua. So 3-aqua, H2O. Chromium 3 chloride. Chromium 3 chloride. Okay, so here also we have two different types of ligand. So it is also not the answer. Next, potassium trioxalato aluminate. Potassium is the cation. Trioxalato aluminate 3. So here there will be 3. Okay. So here I have only one type of ligand, which is an oxalate ligand. So it is a homoleptic complex. So option D is the correct answer. Can you all able to understand? If only one type of ligand is present inside the coordination entity, then it is called as the homoleptic complex. Okay. Clear for all of you? Shall we go for the next question? Shall we go for the next question, students? Yeah. So moving forward with the next question. Yeah, it is an assertion reason type question. It is an assertion reason type. So assertion says that the spin-only magnetic moment value for FeCN6 is 3 minus and 3 minus is 1.74 Bohr magneton, whereas for aqua complex it is 5.92. And reason is in both the complex ion is present in +3 oxidation state. So can you find out the answer? What is the oxidation state of ion in both the complex? So here X minus 6, which is equal to -3. So X is equal to +3. And here also water is a neutral ligand. So X is equal to +3. Oxidation state is same in both. But what about the magnetic moment? In Fe, in Fe3 plus, we have 3d 5 electron and 4 is 0. Okay. This is the configuration. This is the configuration for Fe3 plus. And now what we have to do according to valence bond theory, we have to look into the ligand. We have Cn minus ligand. Cn minus means all the electrons will go and get paired up, right? So if they are pairing up with each other, then what we will have? We will have 2 electrons here, 2 electrons here and 1 here. So we have only 1 unpaired electron. So the magnetic moment will be 1.74. Okay. Then here in case of second complex, see, we have H2. Cn is a strong field ligand, so pairing up takes place. But H2O is a weak field ligand, so no pairing takes place. All the 5 unpaired electrons remains as such. Okay. So the number of unpaired electrons will be 5 and the magnetic moment will also be 5.92 Bohr magneton. Okay. Spin only magnetic moment is also 5.92 Bohr magneton. Assertion is correct. The reason statement is also correct. But the reason is not the correct explanation for the assertion. Option D. You know why? Why reason is not the correct explanation? Not because both the complexes are having +3 oxidation state, the magnetic moment value changes. It is because of the ligand. Okay, it is because of the ligand, the magnetic moment value changes for both, not because of the oxidation state. So both the statements are correct only, but the given reason is not the correct explanation for the assertion. Clear for all of you? Any doubt from this? Bishan, Christina, Jain Viram Nagar students? Okay. So I'll go ahead with one more question. Which complex compound is most stable? Which option is correct? Which complex compound is most stable? Which complex compound is most stable? Option A, B, C, and D. Which is stable? Can you let me know the answer in the chat box? Can you let me know the answer in the chat box? So you can take 1 minute to solve this question. Find out the answer and let me know the answer in the chat box. So this is the correct answer, students. It is option B. Okay. It is option B. Because in option A, we have monodentate ligand. In option C also we have a monodentate ligand. And in option D also all the ligands are monodentate. But only in option B we have a bidentate ligand. Only in option B we have a bidentate ligand. Bidentate ligand means they have the chelation effect. What is meant by chelation? It is called as ring formation. Chelation means ring formation. Okay. So the ring forming ligands are highly stable. Okay. So they will give more stability to the complex. So if a complex is having a bidentate ligand or a polydentate ligand in it, then that particular compound will be more stable compared to the complexes which have only the monodentate ligands. Okay? Clear? So now I'll go with one more question. The IUPAC name of the potassium K3CO C2O4 thrice is. The IUPAC name of K3CO C2O4 thrice is. So we need to find out the oxidation state. Before moving on to the IUPAC nomenclature, we need to go for the oxidation state, right? So we have to find out the oxidation state of cobalt. So cobalt is taken as X. And potassium, for each potassium, the charge should be +1. And we have 3 potassium. So it is +3 plus X. And this C2O4 is an oxalate ligand. Okay. For each oxalate, the charge should be -2. Charge given should be -2. So 3 into -2 is -6, which is equal to 0. Okay. And from this, X is equal to +6 minus 3, which is equal to +3. Which is equal to +3. So +3 is the oxidation state given in all the option. Now you have to go for naming. So potassium is the cation. So potassium, leave some space. We have 3 oxalate ligands. So it is trioxalato. Okay. Potassium is a cation and the complex is the anion. So if the complex is an anion, then the metal should end with ATE. Right? Cobalt should end with cobalt. ATE means cobaltate. So it is potassium trioxalato cobaltate 3. So it is given an option C. Okay, it is given an option C. So option C is the correct answer for this question. Okay. So we have some more questions also. So that I will try to solve in the upcoming classes if we get some time. Okay. So with this, I would like to wrap it up the coordination compounds lesson. So from the next session onwards, we will start with the new chapter. Till then, take care. Thank you, students. So you can give your answers in the poll which I am launching. Thank you so much. Thank you so much. See you.